Hello everyone. So today we are back with our second electromagnetism session. Sorry it's been a long time. So today we will be starting with vector form of Coulomb's law. Okay. So till now we discussed all the properties of charge, including the conservation of charge, quantization of charge, and everything else. And we haven't have any examples, and I think I don't need to do that. I don't need to do any examples on any topic, I guess, because I think we are not studying for an exam perspective. It's just for basic knowledge that anyone can have. So let's start with it. So today's first topic would be vector form of Coulomb's law. So I guess I told you the Coulomb's law last video. If I had not, I'll tell you again. So it won't be a big problem. So what is Coulomb's law? Let me just wait. Let me just do it. Coulomb's law. So what is Coulomb's law? The thing is, when you have two charges in a system, so those two charges exert force on each other, and the force is formulated by using Coulomb's law. So it states that the force between charges, electrostatic force rather say, is directly proportional to the product of charges, and it is inversely proportional to the square of distances between them. So it's like exactly similar to what we see in the gravitational law. So what do we get here? Fe equal to proportionality constant times Q1 Q2 divided by R square. Now the thing is, this K here is called Coulomb's constant, and it has a value. It is generally written as K is equal to 1 upon 4 pi epsilon naught. This epsilon naught is called permittivity of free space. There is another thing called mu naught. It's a permeability of free space. I think I told you about this. I don't really remember. It's been a long time. So please carry on. If you have already studied this, you can just skip the part and can move to the vector form, which we will be discussing in like few minutes. So this K has a value of 9 times 10 raised to power 9, and epsilon naught, if you calculate it, you can use this whole thing and calculate. You can take 4 pi here, you can use pi equal to 3.14, so you will get epsilon naught equal to something around 8.85 equal times 10 raised to power minus 12, around this. So I think you will get it. You need to remember these values for solving questions, which we are not fulfilling that purpose right now. So I guess it's all for now about Coulomb's law. Now let's discuss about vector form of Coulomb's law. We need to draw some lines. Good lines are around here. We will do that, and then we will discuss the law. Okay, so let's make a kind of a Cartesian graph. Okay, for vectors we usually draw it and show it with arrows, so it really works for us, and it will be shown like a position vector as in gravitation, because we need positions of these two. Okay, so let's first point them out. Suppose this is the charge Q1 and this is the charge Q2, and let's make the line a little small. Let's take the line from origin to here, and the second vector from origin to here. Okay, we need to draw arrows. Arrows are important. These are vectors. These are position vectors basically. So let's write here. For example, this is R1 for Q1. This is Q2 and it has a position vector R2. So these are the position vectors of these two charges. Now we have to find the relative position vector between them. So these two does not represent any kind of distance between these two charges, and we should probably, I hope you know about the vector law of addition. We will use the triangle law and find out the position vector, sorry, the relative position vector between these two. The green line which you see here is what we are trying to find out, and we will call this as R, simply R. This is R vector. So now according to triangle law, R1 vector plus R vector should be equal to R2 vector. So if we write it, R1 vector plus R vector equal to R2 vector. So from here, R vector can easily be seen as R1 vector minus, sorry, R2 vector minus R1 vector. That's it. So this is what we define as R vector, the difference between the position vectors of both of the charges. And now we know from Coulomb's law the magnitude of charge. Okay, I'm talking about magnitude of charge. I'm not talking about the direction of the force. I'm talking about the magnitude of the force. Sorry for what I said earlier. It's not magnitude of charge, it's magnitude of force. Would be K Q1 Q2 by R square. Okay, and we have two ways to write it too. If we write it force 1, 2, it means force on 1 due to the second charge. Okay, and if we write it as force 2, 1, force on the second charge due to first charge, which is obviously going to be equal, can be seen through this equation, or you might consider the Newton's third law of third law of motion. Okay, so that every force has an equal and opposite reaction. Every action has an equal and opposite reaction. So basically that. So let's calculate any one of these. Okay, and the only difference between these is when we talk about the directions of these. Okay, so F12 will be a vector, of course, will be negative of F21 vector. The opposite direction it will be. So it doesn't really matter what we say, the magnitude is same, the force is same in value, but the directions are different and opposite, as according to Newton's third law of motion. Completely follows that. So it's kind of let us just first define. Okay, we all know, I think you must know about unit vectors. Unit vector, for example, R cap, defined as a unit vector as R vector divided by magnitude of R vector. It has a magnitude of net equal to 1, and the direction is of whatever the vector we are talking about, in this case R vector. So F1 of 2 is equal to K Q1 Q2 by R square times R cap. If that's it, then F2 of 1 would be K Q1 Q2 divided by R square into minus r cap, which means the negative of the same unit vector. So now let's just take any one of these. Let's just take f1 f11 on due to 2. Okay, so k q1 q2 divided by r square remains the same. Now we change the r cap, which is here, this r cap, we have to change this r cap, okay, into the standard form which I wrote here. You can see this, so let's just put it. We will put it as r vector divided by magnitude of r vector. So now when we talk about squares are already the square of magnitude. If we simply square the vector, or if we take the magnitude and square the vector, it's simply the same. So we can take it as the magnitude of the vector, and its square is being written in denominator already in the equation of force. So it can be written, now we have 1 here and powers of 2 here, so it would be cube down there, power 3, and above would be the r vector divided by now the argument, you might think that it's dimensionally wrong. It's not. It's because you might be thinking that it's cube down there, and if we take force and we talk about dimensions, it shouldn't be cube, it should be squared. But you can see there's r vector above here, and you might argue again it was r cap already, but I told you r cap has a definition of unit vector, which is the same vector divided by the same vector. Units cancel by the magnitude of same vector, units cancel, and it is unitless. So the unit vectors are unitless. I mean, unit vector are called unit vector because they have the value of 1. It's not because they have any unit or something. They are basically unitless, dimensionless, so they don't contribute to any kind of dimension in the force. And same here, one of the r is being cancelled by one of the r in numerator, so it doesn't make any difference. So now you know how to define force in vector form. So I think we have completed the vector form. Okay, so it's kind of a very big leap for now, because it's a long way ahead. We have to, now looking at my notes, we will be proving electric fields, electric forces due to different shapes on different kinds of objects and things, and we will also define electric field. Now it's also our thing remaining that we have to discuss Gauss law. We have electric flux to discuss, and there are a few more things like simple harmonic motion and different kinds of mechanics problems included in electromagnetism, and it would be fun. But we will conclude the lecture here with just a little bit of revision. So what we discussed today is, first I told you what is Coulomb's law. It's basically it. Second, so it's basically it. Then secondly, we discussed the vector form of Coulomb's law. We did not do much today, but videos are coming short, and I will try it to be, because short videos feel better to watch and don't waste much of your time. If you are just doing it for fun, you might think, why waste much time if we are just doing it fun? So videos are going to be short. Watch it whenever you want, or you might even skip it, because we are taking short topics in it and you don't have to find the topic in my videos. So yeah, that's it. After flux, we will be done with this chapter, except for a few more problems I would like to discuss, because they are very interesting, not from exam perspective, it's just for fun. And then we will proceed to understand the potential of electromagnetism. In electrostatics, there is no such thing like magnetic potential in my knowledge. So till my knowledge, I can tell you about electric potential, and we will be carrying on to the next topic, which is magnetism. and a few more. So yeah, thank you, and hope your day goes well. Thank you. Bye.